When you close your eyes and, just picture an earthquake, what do you actually see?
Oh, man. I think most people picture absolute terrifying chaos, right?
Yeah, exactly. I mean, if you're anything like me, you see highways buckling into these massive waves of concrete,
Yeah, skyscrapers swaying wildly,
alarms blaring everywhere, the whole world just seemingly tearing itself apart at the
like
seams.
a bomb went off.
Right. We see the aftermath on the news, and it looks exactly like an explosion. But what if I told you, and this is what we're really getting into today for this deep dive, what if I told you that all of that destruction boils down to one incredibly simple, almost boring physical action?
Just a piece of rock deep underground breaking. That's really it.
That is it, just a rock breaking. And welcome to today's deep dive, where we are taking this terrifying, chaotic phenomenon and, well, we're stripping it down to the bolts. We have some incredible source material today that completely breaks down the mechanics of earthquakes.
It's such a fascinating look at the science
Hmm.
because it is essentially the ultimate geological butterfly effect.
The butterfly effect. Yeah, I like that. Because to really understand the ground beneath your feet and why it sometimes tries to kill you, we have to travel miles below it.
You start with this one highly localized, totally mundane mechanical failure. Just two pieces of stone finally snapping past each other.
And the physical consequences ripple outward to literally alter the course of human history. So our mission today is to change how you, the listener, look at the ground you walk on.
And to get there, we really have to fundamentally rethink the Earth itself. The most shocking realization when you look at the source material is that the Earth's surface isn't a solid shell.
Right. It's not this complete, perfect eggshell protecting us from the molten inside. It's actually cracked.
Deeply cracked, shattered into these massive puzzle pieces that we call tectonic plates.
And those plates aren't just sitting there, they are floating.
Yeah, they're floating on the mantle. So below the crust, you have this churning, just unimaginably hot layer of semi-solid rock.
Like a really dense lava lamp.
Exactly like a lava lamp. The heat from the Earth's core drives these massive convection currents in the mantle, and those currents physically drag the tectonic plates along the surface.
But, and I think this is where people's intuition fails them, we aren't talking about highway speeds here. These continent-sized slabs are moving at a glacial pace.
Very slow, maybe a few centimeters per year.
The source material used a great analogy for this. To put that in perspective, that speed, a few centimeters a year, is roughly the speed at which your fingernails grow.
Which is wild to think about.
Yeah.
You've got whole continents pushing, pulling, and sliding past each other at the speed of growing fingernails.
So if the edges of these plates were, I don't know, perfectly smooth, like greased glass or ice, they would just glide past one another silently. We wouldn't even notice.
But nature isn't smooth. Not at all.
Right. We have to visualize what these boundaries actually look like. We aren't talking about two flat, polished edges rubbing together.
No, we're talking about jagged, rough, mountainous faces of subterranean rock grinding directly into each other.
Which introduces the single most important force in this entire deep dive, friction.
Friction is everything here. When these two rough edges meet, they don't glide. They catch, they grind. Eventually, they just get completely locked together by that friction.
But the plates themselves are still being pushed, right?
Oh, yeah. The main bodies of the tectonic plates are relentlessly being dragged by those mantle currents. They are still trying to move those few centimeters a year, but the boundary, the fault line itself, is completely stuck.
And this is where the danger actually begins, because the force pushing those continents doesn't just disappear just because the edge is stuck.
Physics dictates the energy has to go somewhere.
Exactly. So instead of movement, you get strain. The strain begins to accumulate in that locked rock, and not just for a few days or a few weeks.
No, this strain accumulates for decades. In some places, for centuries.
Which is so hard to picture. To really grasp what's happening underground during those centuries, the source points out that we have to fundamentally rethink our definition of rock.
Because at a human scale, rock is the ultimate rigid material.
Yeah, if you hit a piece of granite with a hammer, it chips. Or it shatters. It definitely doesn't bounce.
But at a planetary scale, it's different. When you put solid rock under millions of tons of pressure over hundreds of years, it actually behaves elastically.
Like a bent stick.
Exactly like a bent stick. Or a wooden bow being drawn back by an archer. Miles and miles of solid subterranean stone literally flex and warp.
They just silently absorb all of that kinetic energy from the plates without actually breaking. I had to sit with that visual for a while when I was reading the prep material.
It's completely counterintuitive.
It really is. The idea of the ground below us slowly bowing like a piece of flexible wood. But, a bow can only be drawn back so tightly.
Right, a stick can only bend so far before something gives.
And at some point, the accumulated strain of all those decades of planetary pushing simply exceeds the sheer strength of the friction holding the rock together.
And that exact microsecond is the moment of rupture. The friction is finally violently overcome.
The rock physically snaps.
It snaps and slips. The two sides of the fault line jolt into a new position to relieve all that built-up stress.
And all that energy, decades or centuries of planetary force that was stored in that bent stick of rock, is released in a matter of seconds.
That sudden, violent release of stored kinetic energy radiating outward, that is the earthquake.
The sheer scale of the time mismatch is what I think makes it so incredibly destructive.
How do you mean?
Well, you have this slow, silent energy storage taking, say, 300 years, and it culminates in a violent release that takes maybe 20 or 30 seconds.
Oh, absolutely. It's a massive compression of time.
It's like winding up a jack-in-the-box in ultra-slow motion for centuries, and then the lid pops open in half a second. All of that time, all that force, compressed into a single moment.
That time compression really is the engine of the disaster. And to navigate how that disaster unfolds, the source material emphasizes that we need to define exactly where that engine is located.
Right, the geography of it.
Yeah, the actual three-dimensional underground location where that rock first snaps.
Yeah.
The exact point of the rupture.
It's called the hypocenter, right?
Yes, the hypocenter. Or sometimes you'll hear scientists call it the focus.
But wait, when we watch the news after a quake, they always talk about the epicenter. They show a map with a red dot and say, here's the epicenter.
They do, and there's a practical reason for that. The hypocenter might be 10 or even 50 miles straight down into the crust.
You can't exactly point a news camera 10 miles underground.
Exactly. So the epicenter is just the point on the surface of the Earth directly above the hypocenter. It's the 2D dot on the map for the public.
Got it. Okay, so the hypocenter snaps, the energy is released, the main event has happened. But the geology of a fault line dictates that the event is actually far from over.
Because the rupture itself physically changes the landscape of the fault line.
Which leads us to a massive, massive failure in how we talk about these events. I'm talking about the word aftershock.
It is a genuinely terrible piece of public relations for a deadly phenomenon.
It really is. When you hear the word aftershock, your brain immediately thinks, okay, phew, the worst is over, the earthquake is done, and these are just the little leftover rumbles.
It implies this totally false sense of security.
Right. But aftershocks are not a separate geological event. They aren't leftovers.
No, they are literal earthquakes. It is just more rock breaking.
Let's unpack the mechanism of why they happen, because the source explains this so well. You have the main rupture. The two sides of the fault jolt into their new positions. Why does it keep shaking for months afterward?
Because that massive sudden movement redistributes an immense amount of stress onto neighboring sections of the fault.
Okay, so it's shifting the burden.
Think of a zipper holding a completely overstuffed suitcase together.
Oh, I've been there.
We all have.
Yeah.
If one tooth of that zipper violently snaps, the pressure inside the suitcase doesn't just disappear.
Right. It instantly transfers to the teeth immediately next to the broken one.
Exactly. You've just shoved a huge amount of strain onto adjacent rock that might have already been right at its own breaking point.
So it's a domino effect. The first snap forces the next section to snap, which forces the next section.
Precisely. Those neighboring sections fail, in turn. Those are the aftershocks.
Yeah.
The fault line is violently trying to settle into a new equilibrium.
And the terrifying reality, and people really need to hear this, is that aftershocks can occasionally be stronger than the main shock.
Which is an absolute nightmare scenario for first responders and survivors.
You survive a massive quake, your house is damaged, but hey, it's still standing. You think the worst is behind you, so you go back inside to salvage your belongings or sleep in your bed.
And then an even larger aftershock hits and brings that compromised building down right on top of you.
That is exactly why returning to damaged structures is so incredibly hazardous. The Earth is still actively fracturing.
And this zipper mechanism also explains foreshocks, which is the exact same process, just in reverse.
Smaller sections of rock failing and transferring stress right before the main rupture.
Right. But the major catch with foreshocks is that they only exist in hindsight.
Because if you feel a moderate shake on a Tuesday, you have absolutely zero way of knowing if that was the main event or if it was just a foreshock.
It could be transferring stress to a much larger section of rock that's going to give way on Thursday.
Hmm.
Scientists can only look back at the data on Friday and say, yeah, that Tuesday quake was a foreshock.
Which deeply complicates public safety. And we're going to get into why prediction is so notoriously difficult later. But for now, let's track the energy.
Let's do it.
We have the hypocenter snapping, we have the domino effect of stress transferring up and down the fault line, the rock has slipped, the energy is out. How does that energy actually travel through miles of solid earth to rattle the teacups in your living room?
It's not just one big messy vibration.
Mm-hmm.
The energy radiates outward in very distinct, predictable wave types.
And knowing the anatomy of these waves isn't just like an academic exercise, it is literally the key to modern human survival.
It's entirely about physics. The energy travels in three main phases. You have P waves, S waves, and surface waves, and they behave very differently.
Let's start with the P waves, the primary waves.
These are compressional waves. The ground actually pushes and pulls in the exact direction the wave is traveling.
The classic visual for this, and I think everyone did this in middle school science class, is a slinky.
A slinky is the perfect visualization.
Right. If you stretch a metal slinky out across a long table and you give one end a sharp forward shove, you see a wave of compressed coils travel all the way down the line.
The coils bunch up and then spread apart.
Yeah, moving forward and backward in the same direction the wave is moving. That is exactly a P wave moving through rock.
It moves through the solid earth, much like sound waves move through the air.
Mm-hmm.
Now, the defining characteristic of P waves is their sheer speed.
They're the fast ones.
They're the absolute fastest seismic waves.
Yeah.
No matter where you are, the P wave will always hit you first. But, and this is a crucial but, they are relatively weak.
Okay, so they aren't the ones knocking buildings down.
Rarely. They might rattle your windows or give the house a sudden sharp jolt or wake you up, but they rarely pack enough punch to cause severe structural damage.
Okay, so the fast, relatively harmless P wave is the opening act. But trailing behind it are the S waves, the secondary waves. And these are a completely different, far more destructive animal.
Going back to your slinky on the table, instead of pushing it forward, imagine grabbing the end and whipping your hand rapidly side to side.
Like a snake.
Exactly. The wave travels forward down the length of the slinky, but the physical motion of the metal coils is lateral left to right, left to right.
That lateral shearing motion is the S wave.
And because that complex side-to-side motion requires a lot more effort to move through solid rock, S waves travel slower than P waves, so they always arrive later.
But that shearing motion is exactly what human engineering hates.
Buildings despise it.
Because buildings are fundamentally designed to handle the downward force of gravity, right? Gravity is holding them to the earth. They are exceptionally bad at handling their foundations being violently yanked sideways back and forth.
That lateral acceleration is what snaps structural steel and shatters concrete. And to help visualize this gap in arrival time between the fast P wave and the slow S wave, I always think of a lightning storm.
Oh, that is a brilliant analogy from the source material. It's like seeing the lightning flash in the distance.
The flash is your fast, relatively harmless P wave.
It hits you instantly, it gets your attention, and it tells you an event has happened.
But the flash also tells you that the heavy, booming thunder, the destructive S wave, is already in motion.
Slowly rolling toward you across the landscape. The flash and the thunder.
And just like a storm, the farther away you are from the epicenter, the longer the gap of silence between the P wave and the S wave.
Before we talk about how we use that gap, we can't forget the final act of this destructive play, the surface waves.
Right, because the P and S waves travel through the deep body of the Earth. But the surface waves, as the name implies, are strictly confined to the uppermost crust.
Traveling right along the surface where we actually live.
They are the slowest waves of all, meaning they arrive last. But they are typically the ones that deliver the absolute killing blow to a city.
Why are they so much worse?
Surface waves cause the ground to physically roll and sway, much like ocean waves on the open sea. If the S waves yanked a building's foundation side to side, the surface waves come in, pick that foundation up, roll it in a circular motion, and drop it.
Wow.
This complex, twisting, heaving motion is what truly tears large structures and underground infrastructure apart.
So we have a very clear sequence. You get the fast, weak P wave jolt, then a gap of time, then the violent side-to-side S wave, and finally, the rolling, heaving surface waves.
That's the anatomy of the shake.
Right. What absolutely blows my mind reading this deep dive is that humanity hasn't just studied this sequence in a textbook. We have actually figured out how to exploit the physics of these waves to save human lives in real time.
It is arguably one of the most brilliant applications of observational science in modern history,
Hmm.
the development of earthquake early warning systems.
We are quite literally racing the geology. Let's break down exactly how this works, because when you first hear about it, it sounds like science fiction. You have this time gap between the lightning and the thunder, between the P wave and the S wave. How do we buy time with that?
It relies entirely on the absolute speed of modern communication networks. We place grids of incredibly sensitive seismic sensors deep underground.
As close to the dangerous fault lines as physically possible.
Exactly. When that hypocenter snaps, the fast-moving P waves radiate outward and hit those underground sensors almost instantly.
You see the lightning flash.
They do. And the sensors immediately feed that data into automated algorithmic systems. Now, here is where the math gets incredible.
Go for it.
In fractions of a second, the system looks at the frequency and the initial amplitude of that very first P wave. By cross-referencing that tiny sliver of data against millions of historical records, the algorithm can instantly calculate the likely size of the rupture area.
And it estimates the severity of the incoming S waves.
Yes, all from that first tiny jolt.
That is insane.
And once the algorithm calculates that a destructive quake is happening, it instantly triggers electronic alerts, blasting them out to all surrounding cities.
And electronic signals, whether that's radio waves, cellular data, fiber optics, they travel at the speed of light.
Which is vastly, vastly faster than seismic waves travel through solid rock.
Yeah.
Even the fastest rock in the world can't compete with the speed of light.
So the electronic warning message easily outpaces the destructive S waves that are currently churning through the earth toward the city.
Depending on how far a city is from the epicenter, this system buys humanity a head start.
But let's be real about what that head start looks like. You're talking about a head start of anywhere from a few seconds to maybe a minute or so.
True.
And I have to admit, my initial reaction to hearing that was almost cynical. A 15-second warning. What on earth can a human being actually do in 15 seconds to save their life?
It sounds trivial.
It takes me longer than 15 seconds to find my shoes.
It is a completely natural reaction.
Mm-hmm.
Human beings are notoriously terrible at utilizing 5, 10, or 15 seconds of unexpected time. Panic sets in. You freeze.
Exactly.
But automated machines are magnificent at it. The true brilliance of these early warning systems, which are fully operational in places like Japan, Mexico, and rolling out across the U.S. West Coast, is that the alert isn't just going to your cell phone.
Right. It's bigger than that.
The alert is hardwired directly into municipal, medical, and industrial infrastructure.
The computers are talking to the computers.
Exactly. Picture what a machine moving at the speed of light can accomplish in 15 seconds. Bullet trains in Japan, traveling at 200 miles an hour, receive the signal and automatically slam on their emergency brakes,
They drop their speed drastically before the ground even begins to shake.
preventing catastrophic high-speed derailments.
That alone saves hundreds of lives.
It does. Now look at hospitals. Alarms sound instantly in operating rooms, giving surgeons a precious 10-second window to pull their scalpels away from delicate tissue.
They can safely pause mid-incision before the room starts violently heaving.
Think about the gas lines. Automated valves on major municipal gas lines instantly shut off, securing the grid to prevent the massive firestorms that historically burn cities to the ground after a quake.
Because it's the fires that do the worst damage usually. Like in San Francisco in 1906, cutting the gas is huge. What about heavy industry?
Factory assembly lines halt. Data centers automatically drop their spinning hard drives into safe states to prevent massive data corruption.
Oh, that's smart.
Elevators and skyscrapers receive the signal, immediately stop at the very next floor, and locks their doors open.
Ensuring people aren't trapped in the shafts when the power grid inevitably fails. Okay, when you put it like that.
And yes, the alerts do go to mobile phones, which gives individuals just enough time to drop under a sturdy desk, step away from glass windows, or pull their cars over.
When you aggregate all of those microactions, all of those automated safety nets deploying across a population of millions, a 15-second warning fundamentally changes the death toll.
It is a triumph of technology. We took that terrifying gap between the initial jolt and the violent shake, and we turned it into a shield.
Okay, so the waves have hit, the early warning systems did their job, the shaking has stopped, the event is over, and now the aftermath hits the evening news.
And the communication breakdown begins.
Yes. This brings us to a massive failure in public communication. The numbers we routinely use to describe earthquakes, the numbers the media feeds us, they are completely broken in the public mind.
They actively trick us into misunderstanding the danger.
And it stems from conflating two very different scientific concepts, magnitude and intensity.
We use these words interchangeably in everyday conversation, but scientifically, they describe two completely different realities.
Let's separate them. What is magnitude, really?
Magnitude is a single absolute number. It describes the total size of the event at its source. It is the total amount of energy released when that underground rock snapped. Think of it like the wattage of a light bulb. A 100-watt bulb is a 100-watt bulb, regardless of where you're standing in the room. The total energy output doesn't change. That's magnitude.
Okay, so what is intensity?
Intensity describes how strongly the shaking was actually felt at a specific location. And intensity varies wildly depending on your vantage point.
Because of distance.
Right. If you are standing 1 inch away from that 100-watt light bulb, the intensity of the light is blinding. If you're standing 2 miles away, you might not even be able to see it.
The magnitude of the bulb stayed the same, but the intensity changed drastically based on distance.
Exactly.
So magnitude is the size of the bomb, and intensity is how close you are to the blast radius.
That's a stark way to put it, but yes.
Yeah.
And the public confusion is deeply compounded by the mathematical scale we use for magnitude.
Historically, everyone knows the Richter scale.
Scientists have largely moved on to the moment magnitude scale.
Yeah.
Because it's far more accurate for measuring massive modern events. But both scales share a mathematical property that absolutely betrays the human brain.
They are logarithmic.
They are logarithmic.
And this is where I think the scientific community needs a PR overhaul. Because a logarithmic scale is a disaster for public safety communication.
It really is, because humans count linearly.
Right. 1, 2, 3, 4. If I hear on the news that yesterday's earthquake was a magnitude 5 and today's is a magnitude 6, my linear brain thinks, okay, 6 is 1 tick worse than 5. It's a little bit bigger.
Like saying a Category 4 hurricane is slightly worse than a Category 3.
Exactly, but that's not how this scale works at all, is it?
Not even close. And that assumption leads people to drastically underestimate the danger of a larger number. Because it's logarithmic, a single whole number step on the scale does not mean 1 unit more.
Okay, break down the math for us.
In terms of physical ground motion, how far the dirt actually moves, each whole number step is 10 times greater. A magnitude 6 physically displaces the ground 10 times more than a magnitude 5.
10 times more shaking, but it gets worse, doesn't it?
It gets much worse because the actual energy release, the explosive power scales even more steeply than the ground motion.
How steeply?
The energy release scales by a factor of roughly 32 for every single whole number step.
Okay, I want to use a visual here to anchor this because hearing times 32 doesn't trigger the right level of alarm in my brain. Let's use dynamite.
Okay, dynamite.
If a magnitude 5 earthquake is the explosive energy of a single stick of dynamite, a magnitude 6 is not 2 sticks.
No, a magnitude 6 is 32 sticks of dynamite detonating all at once.
Okay, now step up to a magnitude 7. That is 32 times more energy than the 6.
So 32 times 32.
That means a magnitude 7 earthquake is roughly 1,000 sticks of dynamite. We've gone from a single stick to enough explosives to fill a moving truck, just by going from a 5 to a 7.
The curve is incredibly steep. Now take it to a magnitude 8. That is 32 times more energetic than the 7.
Which is roughly 32,000 sticks of dynamite. You've gone from 1 stick for a Mag 5 to a literal warehouse packed to the ceiling with high explosives detonating all at once for a Mag 8.
And we can take it one step further to fully grasp the extreme end of the scale. The devastating 2011 earthquake off the coast of Japan was a magnitude 9.0.
A magnitude 9, so 32 times the warehouse.
That is roughly 1 million sticks of dynamite. A magnitude 9 releases more energy than tens of thousands of moderate quakes combined.
That is just... It's hard to even picture that level of violence.
The energy release of the Japan 2011 quake was so incomprehensibly massive that it actually altered the distribution of the Earth's mass.
Wait, really?
Yes, it shifted the planet's figure axis by several inches, slightly shortening the length of a day.
It changed the length of a day.
Just slightly, but yes. But because the scale compresses this enormous exponential range of violent energy into small, benign-looking numbers, 5, 6, 7, 8, 9, the public hears 7 and thinks it's just mildly worse than a 6.
The scale was designed to make the math workable for scientists plotting data on a graph. But it fails spectacularly as a tool for communicating imminent risk to a family sitting in their living room.
Exactly.
So we have this highly deceptive number for magnitude, But you mentioned earlier that intensity, how much shaking actually reaches us, varies wildly based on distance. But there is another variable that changes intensity drastically, right?
Yes, depth. Depth is a massive factor.
Tell me about depth.
Remember the hypocenter? The exact point where the rock snaps. That rupture can happen very shallowly, just a few miles beneath our feet, or it can happen hundreds of miles deep within the crust.
So a deep quake.
A massive magnitude 7.5 earthquake that occurs 300 miles down might barely rattle the dishes by the time the seismic waves travel up to the surface. The energy dissipates as it travels through all that rock.
But a smaller quake closer to the surface.
Right. A moderate magnitude 6 that ruptures very shallowly directly beneath a populated city delivers almost all of its explosive energy straight to the surface. It can be absolutely devastating despite having a lower magnitude number.
Which transitions us perfectly to what happens when those waves finally hit the surface. Because if intensity varies based on depth and distance, it turns out your survival also heavily depends on what exactly your house is built on.
The physical dirt beneath your feet dictates how the waves behave.
Geology matters just as much as the earthquake itself.
Local geology is absolutely critical. The seismic waves, the PES and surface waves physically alter their behavior depending on the density of the material they are traveling through.
What's the best case scenario?
Solid hard bedrock is the safest possible scenario. It transmits the waves quickly and cleanly without amplifying them. If your home's foundation is bolted into solid granite, you have a significantly better chance of surviving intact.
The problem is, humans really don't like building major cities on solid granite. For thousands of years, for trade, agriculture, and just historical reasons, we love building our cities on river deltas, coastal plains, and land we've reclaimed from the sea.
We love soft soil.
We do, and seismically, it is a fatal preference.
Loose sediment, sandy soils, and soft mud act like an acoustic sponge that actually amplifies the shaking.
How does it amplify it? That seems backwards.
Well, when the fast-moving seismic waves leave the hard, deep rock and hit the soft surface soil, they slow down. But physics dictates that the energy cannot just disappear.
Conservation of energy.
Right. To conserve that energy as they slow down, the waves increase their amplitude. The height and violence of the shaking becomes drastically larger in soft soil than it does in hard rock.
And this soft soil amplification leads to a phenomenon that honestly sounds like it breaks the foundational rules of reality: liquefaction.
Liquefaction is terrifying.
Under extreme shaking, water-saturated sandy soil can undergo liquefaction and temporarily behave as a liquid. You're telling me the literal ground can just turn into soup?
It sounds like dark magic, but it is pure fluid dynamics, and it is a nightmare for infrastructure.
Unpack it for us. Give us a visual.
Imagine a bucket filled with wet, coarse sand. The individual grains of sand are resting against each other, carrying the weight of the sand above them, and the water is simply filling the microscopic spaces between the grains.
Okay, I've got the bucket.
Now imagine hitting the side of that bucket with a sledgehammer rapidly and violently. That is the earthquake.
Okay, I'm hitting the bucket. What happens inside?
The violent shaking tries to compress the wet sand, but water is incredibly difficult to compress, and it's trapped in those tiny spaces with nowhere to escape.
So the pressure spikes.
Exactly. Because it can't escape, the water pressure inside the soil spikes dramatically. This is called pore water pressure. The pressure becomes so great that it actually forces the individual grains of sand apart.
Wait, the grains of sand are literally no longer touching each other?
No, they're suspended in the pressurized water.
That's wild.
The soil instantly loses all of its shear strength and stiffness. It temporarily becomes a heavy, muddy slurry, a quicksand-like liquid.
And if you have a multi-story building sitting on top of that ground...
It doesn't matter how beautifully engineered the steel frame of that building is. If the ground beneath the foundation turns to liquid, the building will sink into the earth, tilt wildly to one side, or completely topple over intact.
And the source mentions it does bizarre things to underground infrastructure, too.
Oh, it's chaotic. Underground storage tanks, massive sewer pipes, subway tunnels, these are largely full of air, making them buoyant.
Oh, no.
Yeah. When the soil around them liquefies into a heavy slurry, those massive concrete and steel pipes will literally float upward, bursting right through the pavement of the street above.
We have to talk about the classic, tragic case study for this specific geological trap, which is Mexico City.
Mexico City is the textbook cautionary tale for soil amplification and resonance.
Because it's built on a lake, right?
The modern city was built directly on top of the soft, highly water-saturated sediment of an ancient, drained lake bed. Because of this deeply unique geology, the soft sediment literally resonates when seismic waves hit it.
Like sloshing water in a bathtub.
Exactly like that. If you move back and forth in a bathtub at just the right rhythm, the waves get bigger and bigger. That is resonance.
So what does that mean for the city during an earthquake?
Consequently, Mexico City routinely suffers severe, catastrophic damage from earthquakes that are centered hundreds of kilometers away.
Hundreds of kilometers.
Yes. A distant quake on the coast might be totally harmless to towns built on solid rock much closer to the epicenter. But those waves travel inland, hit the soft lake bed of Mexico City, and the basin amplifies the waves to destructive, prolonged levels, bringing buildings down from miles away.
Which brings us to the most sobering realization when you look at all of this data. We've established that the ground can turn to liquid, and we know it shakes violently. But the stark truth is, the planet rarely kills us.
No. We kill ourselves through the way we build.
It is a mantra among seismologists, isn't it?
Earthquakes don't kill people. Collapsing buildings kill people.
The ground shaking itself in isolation is rarely fatal to a human being standing in an open field. The death toll is almost entirely driven by human architecture.
You can have two earthquakes of the exact same magnitude, hitting areas with similar geology, and have wildly different death tolls. Thousands dead in one, 0 dead in the other.
And the difference is entirely dependent on construction standards, building codes, and strict enforcement.
Absolutely.
Let's talk about the main culprit. When you look at the footage of devastation, there is one type of construction that fails catastrophically time and time again. Unreinforced masonry.
Unreinforced masonry is a death trap.
Explain what that actually is.
We are talking about brick, cinder block, or stone walls that have been mortared together without any internal steel reinforcement like rebar.
Just bricks and mortar?
Right. Think about the physical properties of brick and mortar. They are incredibly heavy and they are incredibly brittle. Mortar is essentially just hard, dried mud.
It has great compressive strength, right? It can hold up a lot of weight pressing down on it.
Yes, but it has absolutely zero tensile strength or elasticity.
It cannot bend or stretch, not even a millimeter.
So when the destructive S-waves arrive and begin violently yanking the foundation laterally back and forth, the unreinforced brick wall cannot flex to absorb the energy.
It just fights the force.
It fights the force until the brittle mortar simply shatters into dust. And because the materials are so immensely heavy, the structure fails entirely and suddenly, pancaking downward and crushing whatever is inside in a matter of seconds.
The analogy I use to visualize the difference between bad, rigid construction and brilliant seismic engineering, and this really helped me, is trees in a severe hurricane.
I like that analogy.
Yeah, if you have an old, thick, deeply rigid oak branch, it refuses to bend in the wind. It fights the aerodynamic force with sheer stiffness, and eventually it simply snaps and crashes to the ground. That is unreinforced masonry.
But a willow tree.
Exactly. A willow tree survives the hurricane easily, not because it's stronger, but because it is designed to flex. It bends with a violent force, absorbs it, and whips back into place.
And that is the core philosophy of modern seismic engineering. Well-engineered structures survive by being designed to act like the willow. We want the building to flex and absorb the kinetic energy.
How do we make concrete flex, though?
We use reinforced concrete, weaving flexible steel rebar into the concrete to give it tensile strength so it can stretch without shattering. We use flexible steel frames that can bend significantly without snapping.
And shear walls, right?
Yes, we design shear walls into the core of the structure to resist that specific lateral yanking motion of the S-waves.
But engineering goes way beyond just making the walls bend. Let's dive into some of the more advanced technologies, specifically base isolation, because the mechanics of this are fascinating.
Base isolation is incredible. We test these on massive, warehouse-sized shaped tables.
How does a base-isolated building work?
Base isolation is fundamentally changing the relationship between the building and the earth. Instead of the foundation being rigidly bolted directly to the rock, the building is essentially uncoupled from the ground.
Uncoupled? How?
The structure sits on massive, flexible bearings. These bearings are incredibly complex, often made of alternating, vulcanized layers of heavy steel plates and thick rubber, sometimes with solid lead core in the center to absorb energy.
So the building is basically sitting on giant rubber pucks.
Exactly. When the ground below shakes violently side to side, the rubber bearings deform and shear. They absorb the extreme lateral motion.
So the ground is moving, but the building isn't.
The ground underneath is moving violently, but the building above it stays relatively still, gently gliding back and forth on the bearings, rather than being whipped around.
And for ultra-tall skyscrapers, where base isolation might not be enough to stop the sway at the very top, engineers use tuned mass dampers.
Tuned mass dampers are a brilliant application of physics. If you visit Taipei 101 in Taiwan, you can actually see it.
It's that giant gold ball, right?
Yes. It is a massive, multi-ton, solid steel pendulum suspended near the very top of the skyscraper. It acts as a counterweight.
How does it work during a quake?
When an earthquake or a typhoon wind makes the building sway heavily to the left, inertia keeps the heavy pendulum in place, effectively swinging it to the right relative to the building. The pendulum counteracts the sway, absorbing the kinetic energy and keeping the building upright and stable.
So we have all this incredible science. We have base isolation, steel reinforcement, tuned mass dampers. We absolutely know how to build structures that will survive violent shaking.
We do.
Why are thousands of people still dying under collapsed roofs every time a major quake hits?
The pure, brutal economic reality. The obstacle is not a lack of scientific knowledge. The engineering is fully understood.
The obstacles are cost, political will, and history.
Engineering a brand new building to survive an earthquake is expensive, but retrofitting an existing building is astronomically more expensive.
Because you have to open the walls up.
It requires tearing into walls, inserting steel frames, shoring up foundations. Enforcing modern codes requires robust, uncorrupted government oversight, which isn't present in many developing nations.
And you just have the sheer volume of old buildings.
Yes. The vast, enormous stock of historical buildings around the world that predate modern seismic codes by decades or centuries.
We know exactly how to save everyone living in those brick buildings.
But retrofitting an entire historic city with steel reinforcement is economically crippling for most municipalities. It is an economic and public policy failure, not a scientific mystery.
Let's transition from the cities on land to what happens when this violent hypocenter rupture occurs miles underwater at the bottom of the ocean.
Because tectonic plates don't stop at the beach.
Right. And when they snap underwater, the physics change from shaking dirt to displacing oceans, creating a hidden, terrifying threat, this tsunami.
Tsunamis are a completely different expression of seismic energy. They are typically generated at subduction zones.
Define a subduction zone for us.
A subduction zone is a specific type of tectonic boundary where one dense oceanic plate is actively being thrust underneath a lighter continental plate.
So one plate is diving down and the other is riding up over it.
Yes, and as the bottom plate dives down, friction locks it to the top plate. Over centuries, the top plate is dragged downward, warping and building immense elastic strain.
Like the bent stick again.
Exactly. When that friction is finally overcome, the top overriding plate acts like a giant miles-long springboard. It violently snaps upward and outward, instantly displacing a massive section of the seafloor.
And it's not just moving the dirt at the bottom, it is moving the miles of water sitting on top of it.
It lifts the entire water column.
Wow.
Imagine the sheer, incalculable weight of an ocean that is 3 or 4 miles deep. The earthquake abruptly forces the seafloor up, and that immense kinetic energy lifts billions of tons of water upward all at once.
And gravity has to push that back down.
Gravity immediately pulls that massive bulge of water back down to sea level, and that violent displacement of energy propagates outward in all directions.
Yeah.
That pulse of energy is the birth of the tsunami.
But the way a tsunami behaves in the deep ocean is surprisingly stealthy. It is not a massive towering wave out in the middle of the Pacific.
It's incredibly stealthy, which makes it dangerous. In the deep ocean, all of that displaced energy is spread out over a water column that is miles deep.
So the wave isn't tall.
Because the energy has so much room to stretch vertically, the actual wave on the surface might be less than 3 feet high. Its wavelength, the distance from crest to crest, can be 100 miles long.
A commercial shipping vessel out at sea could have a massive tsunami pass directly underneath its hull, and the crew wouldn't feel a thing.
They'd never notice it.
But that barely noticeable 3-foot wave is carrying a horrifying amount of momentum.
It is traveling at the speed of a commercial jet aircraft, roughly 500 miles an hour across the open ocean.
And then it reaches the shallow water of the coast.
This is where the conservation of energy turns deadly. As this massive high-speed pulse of energy approaches the shoreline, the ocean gets shallower. The front of the wave begins to interact with the rising seafloor.
Friction acts like a brake, slowing the front of the wave down significantly.
But you still have all that kinetic energy traveling behind it at 500 miles an hour. It has to go somewhere.
Exactly. The energy compresses, it can no longer go forward as fast, and it can't go down into the seafloor, so it is violently forced upward.
That subtle 3-foot-deep ocean wave rears up, compressing its energy into a devastating, towering wall of water that can be tens or hundreds of feet high.
Put yourself on that beach for a moment. You are standing there, and you see a phenomenon that frequently precedes the crest of the tsunami. The water suddenly dramatically withdraws.
The ocean literally drains away, exposing a mile of bare seafloor.
Why does that happen?
Think of the shape of a typical wave. It has a high point, the crest, and a low point, the trough. Depending on the exact geometry of how the seafloor ruptured, the low point of the tsunami wave often reaches the shoreline before the high crest does.
So it vacuums the water away?
It effectively vacuums the water away from the coast, pulling it out to sea to feed the massive incoming crest.
And this is where you have to actively fight your own evolutionary instinct to survive. Your human brain is wired for curiosity. When the sea suddenly withdraws, leaving fish flopping on the bare sand and exposing ancient shipwrecks, the human impulse is to walk out and look at it.
It is a fatal curiosity.
Overriding that instinct requires deep, pervasive public education. People need to visualize the danger correctly. When we hear the word wave, we think of a surfer riding a curling cylinder of water that crashes on the beach and then immediately recedes back into the ocean.
A tsunami is not a surfing wave.
Not at all.
It is a massive, sudden, unstoppable rise in sea level. It does not crash and recede. It is a rushing, turbulent, churning river that pushes inland with immense hydraulic force.
It carries cars, trees, and buildings with it like battering rams.
And it keeps pushing inland for 5, 10, sometimes 15 minutes on end before the water finally stops rising.
And crucially, it is never just one wave.
Never. A tsunami is a series of waves, often spaced tens of minutes or even hours apart. The first wave is frequently not the largest.
Returning to the shore to survey the damage or look for loved ones after the first wave recedes has repeatedly proven fatal.
Because the second or third wave can be vastly larger and more destructive.
Given all of this, collapsing masonry, ground turning to soup, oceans rising up to swallow cities, it feels like modern science should be throwing everything it has at predicting exactly when these things will happen.
It's the holy grail of seismology. But we need to address the reality of forecasting, and the scientific consensus in our source material is harsh.
It's important to be relentlessly honest here because false hope leads to bad preparation. We have to separate two very different concepts: long-term hazard forecasting and short-term prediction.
Seismologists are actually excellent at long-term hazard forecasts. By studying fault lines, digging trenches to look at paleoseismology, and tracking strain with GPS, they can identify which regions are at extreme risk.
They can confidently state there is, say, a 70% probability of a magnitude 7 earthquake occurring in a specific region over the next 30 years.
And that data is crucial. It dictates our building codes, it tells us not to build a nuclear power plant on a specific fault, and it guides the insurance markets.
But that's a 30-year window. What the public wants is short-term prediction. They want a scientist on the evening news saying, "Evacuate Los Angeles on Tuesday at 4 p.m. because a magnitude 8 is hitting."
And that level of short-term prediction is currently impossible. And the wider consensus in the scientific community is leaning toward the idea that it may be fundamentally impossible.
Why fundamentally impossible? I mean, we can track a hurricane forming a week out and predict its exact landfall. We can calculate the exact minute a solar eclipse will happen 1,000 years from now. Why can't we predict a piece of rock breaking?
Because of chaos theory and the limits of observation. You can point a satellite at the ocean and watch a hurricane form. You can use telescopes to track planetary orbits in a vacuum. But the hypocenter of an earthquake is miles beneath the solid surface of the Earth.
We can't see her.
The precise moment that a massive fault line finally overcomes friction and fails depends on microscopic conditions. Tiny variations in rock strength, minute changes in fluid pressure, microfractures in the quartz kilometers underground.
It is a level of chaotic detail that we simply cannot observe. We cannot drill a hole and put a sensor every 10 feet along a fault line that is 1,000 miles long and 10 miles deep.
The system is too complex and too obscured.
Let's address the myths then. Because whenever you tell people prediction is impossible, the anecdotes flood in. People say, "But my dog started barking wildly an hour before the big quake hit," or, "What about earthquake weather? It was unusually hot, humid, and perfectly still yesterday before the ground shook."
Those myths are deeply persistent, but we have to dismantle them using the scientific method. Despite a century of desperate, well-funded effort by brilliant minds, no precursor has been found that reliably precedes earthquakes.
For a precursor signal to be scientifically useful, it must reliably happen before an earthquake.
And it must reliably not happen when there isn't an earthquake.
You can't just have false positives all the time.
Exactly. Claims involving animal behavior, weather patterns, or planetary alignments have totally failed rigorous scientific scrutiny.
Dogs bark for thousands of reasons. A squirrel, a car, a weird smell.
You only remember the dog barking if an earthquake happens an hour later. You forget the 1,000 times the dog barked, and nothing happened.
As for the weather, the atmosphere is constantly changing miles above the subterranean rock. The rock 10 miles down does not care if it's humid on the surface. There is zero verifiable statistical correlation.
None.
So the takeaway from the scientific community is clear. Stop looking for a crystal ball. Stop waiting for a warning that isn't coming. The effort, the money, and the mental energy belong entirely in preparation, not prediction. Assume it will happen eventually and build a house that won't kill you when it does.
Preparation is the only variable we control.
Which brings us to our final crucial concept, the illusion of safety. Because at this point in the deep dive, I imagine a lot of listeners who live in places like the American Midwest or Northern Europe or Australia are thinking, wow, this is fascinating physics, but I am so incredibly glad I don't live on a fault line. Good luck to the people in California and Tokyo.
Relying on distance from a plate boundary for total immunity is a massive vulnerability.
It is a dangerous illusion. Australia is the perfect case study for this, right?
It sits comfortably in the deep interior of the Indo-Australian tectonic plate, thousands of miles away from the active grinding edges where the vast majority of global earthquakes happen. Geologically, it is considered one of the more seismically stable continents on Earth.
But stable does not mean immune.
No, because of interplay earthquakes, quakes happening in the middle of the plate.
The interior of a tectonic plate might not be directly grinding against another plate, but it is still a rigid piece of rock being subjected to immense stress.
The violent forces pushing and pulling on the distant edges of the plate transmit stress all the way through the solid interior.
Like pushing on the edge of a large pane of glass, the stress travels through the whole pane.
Exactly. And the interior of a continent isn't a perfectly flawless pane of glass. It is heavily scarred with ancient, hidden fault lines from hundreds of millions of years ago when the continents were forming and breaking apart.
Under enough transmitted stress from the distant plate boundaries, these ancient, dormant faults deep in the interior can suddenly reactivate and slip. That is an intraplate earthquake.
Let's look at the 1989 earthquake in Newcastle, Australia. It perfectly illustrates the danger.
The Newcastle quake was only a magnitude 5.6. Now, in California or Japan, a magnitude 5.6 is a fairly routine event that rattles windows but rarely causes severe, widespread damage.
But in Newcastle, that 5.6 killed 13 people, injured over 100 more, and caused billions of dollars in structural destruction.
Why was a moderate quake so deadly there?
Because of everything we've discussed today coming together in a perfectly tragic storm. First, the rupture was very shallow, delivering high-intensity shaking directly to the surface. Second, parts of the city were built on soft alluvial soil, which amplified the waves.
And most importantly, the building stock was old, unreinforced masonry.
Because they built a city on the reasonable-sounding assumption that earthquakes simply wouldn't happen in the middle of a stable tectonic plate. They didn't build with seismic codes because they didn't think they needed them.
And that is the paradox of stable regions. Earthquakes in these zones are much rarer and generally smaller in magnitude. But the risk to human life can actually be uniquely high, precisely because the population and the infrastructure are entirely unprepared.
They don't have early warning systems wired into their trains. Their building codes historically haven't required flexible steel reinforcement. Their brick buildings are brittle.
So, speaking directly to you listening right now, if you are sitting in a safe zone far from a plate boundary, you might actually be in more physical danger from a moderate, unpredictable magnitude 5.5 earthquake than someone in Tokyo is from a massive magnitude 8.
The person in Tokyo is sitting in a flexible, base-isolated, engineered structure.
You might be sipping coffee in an unreinforced brick cafe that was built 100 years ago with dried mortar. The illusion of safety is a massive vulnerability.
It's a sobering reality check. The ground beneath our feet is dynamic everywhere. No matter where you live, you are living on a planet that is slowly, constantly recycling its own crust.
Let's take a breath and synthesize this incredible journey we've been on. We started miles underground, visualizing the silent, unseen accumulation of planetary strain, building up over centuries like a drawn bow. We witness the sudden, violent snap of the hypocenter, releasing all that compressed time and energy in seconds.
We track the complex race of the seismic waves, the fast P wave acting as a warning flash, the destructive S wave yanking the foundation sideways, the rolling surface waves tearing the ground apart.
We explored how shallow depth and soft, liquefying sediment actively amplify that destruction. And most crucially, we uncovered the stark truth that the numbers on the news often trick us into underestimating the power of the planet.
And that it isn't the shaking ground that takes human lives, but the heavy, brittle structures we choose to build.
The overarching theme here, the true shift in perspective for anyone listening, is moving from a sense of victimhood to a sense of agency. We are completely blind to when the Earth will break. Prediction is a phantom we need to let go of.
But we have nearly absolute control over how we build our world to withstand it. We are not helpless victims of the ground.
When a modern city falls, it is a failure of human engineering, economics, and public policy, not just an unpredictable act of nature.
And as we wrap up, I think that brings up a really crucial question about what we are doing today, right now, as we continue to build our modern world.
It leaves us with a haunting thought about the clash between the immense timescale of geology, centuries of slow, invisible strain, and our very short human timelines of decades of building.
We look back at unreinforced masonry and we realize it was a massive, lethal blind spot of our past. We see it clearly now.
But it forces you to wonder, what standard everyday infrastructure are we building right now, today, that future generations will look back on and realize was fundamentally, tragically unprepared for the Earth's inevitable slow-ticking clock?
Are our subterranean transit networks truly resilient against soil liquefaction? Are our coastal megacities actually prepared for the massive subduction zone tsunamis that only happen once every 500 years?
What is our modern equivalent of the unreinforced brick wall? Something to mull over the next time you look up at a skyscraper or walk past a brick building in a safe city. Thank you for joining us on this deep dive. We hope we've fundamentally changed how you view the solid earth beneath your feet. Keep looking a little closer at the world around you, stay curious, and we'll see you next time.